Okay. Okay, let's see. We've got that going. Okay, I'm going to start calling names, and I'm actually not starting early today because I'm behind schedule. Sorry about that. Let's see. Sarah B. Okay. Claire. Matt. Okay. Luke. Jaden. Okay. Liza. Ethan. Manya. Olivia. Kashal. Diego. Darwin. Oh, Darwin. Oh, perfect timing. Wow. Sean. Okay. Jules. Jules? No? Oh, you okay. Yeah, thank you. Doa. Oh, okay. Gotcha. Matthew. Here. Yeah. Colin. Okay. Emily. Okay. Rennick. Oh, yeah, right. Sarah T. Right. And McKenna. Okay. Okay. Sorry for the late start. Okay, so let's see here. Here's what we were talking about last time, and I'll do a super quick kind of revisitation of what's going on there. There we go. Of what we talked about last time with the chain rule. So it's all about interpreting what the derivative. Oh, come on, you're killing me. Okay, I know I've got to start this over again. I'm sorry. My computer, if I open up my PDF software and then I close the screen and then open it up again, it glitches. Sorry. 2 seconds. Okay, so we are a ways forward here. And of course now, yeah, okay, there we go. Okay, so the derivative, right? What's the interpretation we're taking of the derivative? It's the thing that you multiply by this to get that. So the derivative is a factor here, right? It's what you multiply by the input change to get the output change, yeah? Okay. All right, so with that in mind, we look at a composition of functions and we have various changes. So, that's how much X is changing. And as a result, this is how much Y is changing. And as a result of that, this is how much Z is changing. Okay, well, let's see here. So F prime is what you multiply by that to get that. Right? And then G prime is what you multiply by that to get that. So altogether, right, what have you multiplied by to get from X prime to Z prime? Well, you multiply by F prime and then you multiply by G prime, right? And so we get this, this observation here that the product of these derivatives is what gives you the derivative of the composition. Oh, let's see, let me zoom out. We can fit that all on the screen, right? So dark blue times purple gives you the derivative of the composition. Okay, so that's really all the chain rule is in a single variable context. And then the observation I'm going to make here in the multivariable context, the same deal, right? The derivative, now it's a matrix, of course, is, well, it's what you multiply by an input change to get an output change. It's just that, well, now the changes are vectors, and the thing you multiply by is a matrix, but it's still the thing you multiply by, right? And so really the exact same argument goes through. It's just that now these input and output changes are vectors. The things that we are multiplying by are matrices. And let's see here, I'm trying to use the colors the same. Right, and then the composition then is the product of those two matrices. So same, morally the same result, just interpreted, you know, for the different context. Yes.
So what if the output variables for F is different than the input variables?
Yes.
For G?
Then you can't compose them, and there is no question to be answered. Right. That's right. Now the whole thing comes crashing down. Absolutely. Absolutely. Yep. Yep. Yeah. If there's a square peg round hole problem, then there's nothing to do. Yeah. Great question. Anybody else? Okay. All righty. Okay, so I think that's about where we were last time. And just as a reminder, I like to summarize this as differentiation turns a composition into a product. Right now, it's a product of matrices, as it turns out. But compositions turn into products. Okay. All right, so let's see an example. And I've got one prepared here. So here's a function. We've got x's as the inputs and y's as our outputs. And I've got a second function here where y's are the inputs and the z's are the outputs. And then in order to kind of streamline out all of the sort of extraneous stuff, I'm just going to straight give you the derivative of this function at a certain point, and likewise the derivative of this function at a certain point. Right, and where did those come from? Well, in general, you know formulas for the functions. You have to take various partial derivatives and all that stuff. Okay, and we've been asked to compute the derivative of the composition. Now let's be careful about one thing. We are given df at this point 1, 2. We are given dg at a totally different point 3, 1, 0. Is that okay? Well, in fact, it's necessary. So in particular, this 1, 2 is the where I know df, because that's where I'm evaluating f. It's the value of x1, x2, right? So what does that mean about where g is evaluated? Well, g is evaluated at what comes out, right? And what comes out is this point, y1, y2. See, g is evaluated at what comes out of the f function. So g is being evaluated at the point 3, 1, 0. And that's the point where I know dg. Right, so it's not only okay that these points are different, it is necessary that these points are different. I need to know if this point is called A, then I need to know dg at the point f of A. Okay, and you can of course see that on the picture back here. The function f is being evaluated at the point A. I need to know f at A. I need to know df at A. G is evaluated at f of A. So I need to know dg at the point f of A. Okay, all right. So punchline, then I'm given exactly the matrices that I need in order to be able to plug into our newfound chain rule, product of matrices. Now, the one little bit landmine that is in this problem, and I'm going to confess, I sort of did this on purpose. I gave the matrices to you in what you might call the backwards order. So df, oh, whoops, colors. df, I gave it to you on the left, but it needs to be on the right in the product. And dg, I gave it to you on the right, but it has to be on the left in this product. Now, why? Well, it's all about which one acts first, right? And when we write functions, we tend to think of them as left to right, but when we multiply matrices, they act right to left. It's weird, but this is first, as is that. And this is second, as is that. Excuse me. Okay. Everybody with me? So all I can say about that is heads up. Yeah, you always got to be thinking about, okay, which one's first, which one's second. And then, so don't think in terms of left and right. That's a problem, right? Just think in terms of which is first, which is second, and then remember which way, how do you translate first and second into, well, whatever picture you happen to be looking at, and then, interpret appropriately. Okay, with all of that said, DF, right, there it is, boom. BG, there it is. And we just have to multiply these matrices. That's something I'm sure you all remember how to do. And there you go. There's your derivative matrix. So we literally, derivative of a composition is a product of the individual derivatives. Okay. Now, the question did also say, not just compute the derivative matrix, but also compute the partial of Z3 with respect to X1. So I'm going to have to zoom out one spot here. So partial of Z3 with respect to X1. Well, we're taking a partial with respect to X1. X1 is the first input variable. Partials with respect to input variables correspond to columns. And so the fact that it's partial with respect to X1 means I'm looking in the first column. I am taking the partial of Z3. Z3 is the third of my variables, right? Variables correspond to rows. So I'm going to be looking in the third row, output variables, that is, correspond to rows. So third row means that. And so this partial that I was asked for, that specific partial, is that specific entry in the matrix. And so it's 3. Is everybody happy? Okay. All righty. Okay, so a couple of quick observations and examples. In the special case where, I guess I can zoom back, where you are looking at where there's a single input variable to the first function. Well, neat fact, if there's only a single input variable, if you were to think of that input variable as being time, then notice you've got here position as a function of time. That's a parametric curve, and you can think of it as a parametric curve, right, which allows for a certain convenient and desirable method of visualizing what's going on. Right? And then furthermore, the composition, right, gives you position also as a function of time. And so you can think of that as being a parametric curve, right? So you can think of, all you need in order for this to be the case is that there's a single input variable to the first function. And when that happens, you can think of what's going on here as I've got a function from a domain to a target, and I am apparently moving around as described by a parametric curve in the domain. And I am then, as a result, I have an image that is moving around as a parametric curve in the target. And in fact, the chain rule turns into, well, let's see here, this matrix here, right? The derivative of our first function is, you write down the derivative matrix, and oh my gosh, look at that. It's the velocity vector, right? It's literally giving you the velocity in this of this parametric curve. And then likewise, the derivative of the composition is the velocity of that output parametric curve. So what the chain rule says in this special case where you have just a single input variable for the first function, what it says is that the derivative matrix the derivative matrix relates input velocities to output velocities. We already knew that. right? But it's kind of neat as a confirmation, you know, a check that the chain rule recovers a previously known fact about derivative matrices. Right? So the following example is really just kind of taking advantage of that, but this example could have made sense in the previous sections where we already knew what derivative matrices do, right? They relate input velocities and output velocities. So here I have a function. And notice I've got two input variables and three output variables, right? Notice I've got a picture here. Domains over here on the left, targets over here on the right. Right, so this is that, you know, again, what I like to call the literal picture of the function. And in the domain, I'm at this point 2, 1, and moving with velocity 4, 3. And the question is to compute the corresponding output velocity. I've got the input change. I want the output change. Well, we multiply by the derivative matrix. Right, and the derivative matrix, straightforward computation, you know, a little bit tedious. I've got to take various partials, right? I have to take, for example, all of the x1 partials to get that first column. And then I've got to take all of the x2 partials to get that second column. And then, of course, plug in the point where you're at, right, that A point, plug that in, get the derivative matrix where you are, you know, relevant to where you actually are, and then multiply. Everybody good? Okay. All righty, here's another special case. This is sort of a special case of the special case. And so the previous special case was there was a single input variable. We could think of that as time. That means we have a kind of parametric curves in the other two spaces. Well, yeah, but what if the output of the second one also has just a single value? What happens there? Well, not much different. I can still think of this as you know, the input variable is time. I can think of this as that I'm moving around in the Rn, and then its image is moving around. Well, it's now moving around on just the number line. So still I have output velocity and input velocity being related by the derivative of that function. Really, the only thing that's different is that this derivative matrix now has, as it does, a single row, and so I can think of that matrix vector product as being a dot product. And again, old news, right? We've seen this before. So this is just the same thing, but instead of the derivative being thought of as a matrix multiplication, now the derivative can be thought of as a dot product with this special gradient vector. Okay. All right. And so, you know, again, example now, so this example would have made perfect sense in, you know, a couple sections back when we were talking about linear approximations and you know, the derivative matrix and the interpretations of the derivative matrix. So, you know, again, if I let's suppose that instead of a vector valued function, let's suppose I'm just keeping track of temperature. Temperature is real valued. It's a number. It's not a vector, it's a number. Right? So, well, how fast is that temperature changing? Well, I need to know about my motion in the domain. Well, I'm at this point and moving with that velocity. And dot product with the gradient. My picture's getting messy. Dot product with the gradient. Evaluated, of course, at the point where I'm at. And there we go. How we doing? Okay. Okay, so going to give you a different point of view on the chain rule. I'm going to take a general case where I've got several inputs that lead to several outputs, which become the inputs for another function, which itself has several outputs, right? So this is our sort of general case. And I can look at the partials of this function. That gives me that matrix. And then I can look at the partials of this function, which gives me that matrix. And then if I'm interested in the composition, right, the thing that turns the X's into the Z's, you know, what can I say about its derivative matrix? Well, its derivative matrix is the product of the original two, right? So this is our good old chain rule previously noted. And all I'm going to do is ask what happens if I think about this product matrix one element at a time. Let's look at just one single element of that product matrix. Well, I know how to compute a product, all right, an element in the product. Y'all know that I'm a big fan of thinking about matrix multiplication as linear combinations. But as it turns out, not here. As it turns out, the good old dot product point of view, you know, row dot column is going to be super convenient. It's exactly what we need in this case. So let's multiply that out. That element, let's see, let me color code a little bit better. I take this row, the various partials of Zi with respect to the various Y variables, right? And they get multiplied sort of one at a time by the entries in that column, which are of course the partials of the Y's, various Y's with respect to Xj. Notice all of these are Zi's. So all of these are Zi's. Right, all of, let's see, we have an Xj there. We have, these are all Xj's here. Right, all we have is that, well, there's a bunch of terms that kind of relate to those, and they, you know, multiply out like this. Everybody good so far? Okay, so before we go on and there's a neat observation about how you can reinterpret this. I do want to take a pause and emphasize what you cannot do. And that is, you cannot think of this as a cancellation. You cannot think of it as, oh, well, yeah, you know, you remember they used to talk like this in single variable calculus. It's kind of like you're just canceling the partial y1s or something. And notice that then you have, you know, the correct numerator and the correct sort of remaining denominator. And, oh, well, wait a second. What about all this stuff over here? Right? What's going on with all those? Right? You absolutely just can't make that. You can't make that cancellation. And this is concerning to a lot of students who look at that and say, well, but why can't you? I mean, we've been canceling terms from numerators and denominators of fractions forever. Right? And this is part of why I like to remind students these aren't really quite actually fractions, because a fraction, saying that this, for example, is a fraction suggests that this is a well-defined thing by itself, and it's not. So that's really the point here. This y1, this partial y1 there, right? Let's look at it down here. That partial y1 is not the same thing as this partial y1 here. They are different because they're part of different stories, right? So let's think through now what is this a part of, you know, this thing here is a part of what story? Well, it's a part of this story here where I'm taking the partial of Zi with respect to, well, that specific y1 variable, which therefore insists, you know, in that story, you know, while I'm thinking about this thing, all of the other y's are required to be constant. Right. So in, you know, as I compute this thing, I've created a scenario where y1 is allowed to change. All the other y's are constant. Notice I have no idea in this story what's happening to the x's. In fact, I don't even know, as I consider this partial derivative, I don't even know if it is possible for there to be some motion of the x's that would give me this scenario where the y's do what I'm suspecting, what I'm, requiring. So this is a very sort of narrow, sort of like, forget about the x's. I've never heard of the x's. I'm just going to consider this particular scenario. Y1 is changing. All the other y's are constant. Hypothetically, then what happens to zi? Okay. Now compare that to what's happening in this other story over here. This other story, I'm holding a bunch of x variables constant. I am changing xj. Well, here's the thing. When you change xj, I'm sorry, but those other y's are not going to be constant. Right? So they're different. I mean, to be fair, yes, each one of these represents a change in y1, but there are changes in y1s in different situations. It's like you can't take, one problem over here and another totally different problem over here. In this question, x turns out to be 3, and in this entirely different disconnected question, x happens to be 17, and then compare and say, hey, wait a minute, what is? Right? They're totally different questions, and these are totally different scenarios as well. So you just can't cancel those things. It doesn't make any sense. Everybody with me? So this is a very, very dangerous circumstance. I mean, a lot of students make this mistake, on tests and everything, and will, literally kind of cancel that, and then just kind of all the rest of this just kind of disappears, and it's just wildly, wildly wrong. Okay, so please don't step on that landmine. And let's see here. Let me get back to, yeah, here we go. Okay, so back up to where we were. This element of the product matrix is computed as a dot product of that row with that column, thus giving these various terms. So how else might I interpret this? And here's the way I want to think about it. This same equation. Think about the variables themselves, and don't forget f turns, the x's into y's, and g turns the y's into z's. Right, and so I'm just going to make a sort of a little roadmap of all of our variables, and we know we're interested in how. Let's see here, how zi changes. So let's look at that eventual output variable, and we're interested in how it changes with respect to xj. Right, so there's that input variable, and okay, well, as I change that variable, what's going to happen? I claim a bunch of things happen when you change xj, with the understanding, of course, now that all these variables over here are all constants. Right? What happens when you change xj? Well, all of these variables here are going to change. Each one of which, right? I mean, just looking just at y1, just for the moment, just for a quick moment, as y1 changes, then zi is going to change. But the thing is, the fact that y2 is changing is going to make zi change, and et cetera, et cetera. The fact that ym is changing is going to make zi change, right? So the point of view I want to give you is you can think of changes propagating along paths, right? So here we have a path along which a change can propagate. So as xj changes, that causes a change in y1. As y1 changes, that causes a change in zi. And that's really what's going on with that term right there. Right? That's saying, let's see here, color-wise. This part right there is that factor, and then the next step there is that factor. What do you think? That makes sense? So that term is a way of keeping track of changes that propagate along that path. and then et cetera, right? Various other variables. And then finally, let's see here, colors. Yeah, use orange. That term is talking about changes that move along that path. So I'm a big believer in this point of view. I think this is really nice. Now, there are circumstances when the power of matrix multiplication is invaluable and you got to have it. And I think this is the best way to understand, why the chain rule works. This point of view here, I really think the matrix point of view is super, super valuable. But sometimes where am I? Yeah, here we go. Sometimes if you've got, very specific variables, and if you just want to know just this one partial derivative, and I don't really need to bring up all the big gun power of derivative matrices and matrix multiplication that would compute all of the partial derivatives. I don't need all the partial derivatives. I just want that one, right? Then understanding this idea of the intermediate variables, right? All the paths that we're interested in propagate along one of these paths, namely through one of these intermediate variables, and each one gives you a term, right? So there's what you might call here the y1 term that goes through y1, et cetera, and then this, you might call this the ym term that goes through this variable ym. And that's you can just write it down. You can just see it directly from your sort of roadmap of variables. It's very handy. Okay, let's see an example. So here's a couple of functions. We've got f, we've got g, and we've got explicit formulas. So, if we wanted to, we could take a deep breath and write down all the partials of all of these variables, all with respect to all the others, as per the usual pattern, and we could multiply the matrices. But the question doesn't ask me for the derivative matrix. The question just says, look, I just want the partial of z2 with respect to x2. That's it. Intermediate variables is going to be faster there. So now first, let's make sure that we understand what's going on. By the way, this is something that I wish books would encourage more, but I strongly encourage you to write down not just the formulas for your functions, but write down what I like to call the roadmap of which variables go where, which variables relate to which other variables by way of what. Okay. And so here we go. F turns these x input variables into these y output variables, right? x1, x2, x3 are the inputs, and then y1, y2 are its outputs. And then G turns those outputs, y1, y2, into further outputs, final outputs, z1, z2, and z3. So notice I've got that now represented on my little diagram, my little roadmap down here. And with that noted, I see that I've been asked again for a partial of, let's see, I'll do it like this, partial of z2 with respect to x2. Well, there's z2, there's x2. I can immediately see from this picture what my intermediate variables are. My intermediate variables are y1 and y2. There are two paths along which changes can propagate from x2 to z2. Two paths means two terms. In fact, let me color code better. The y1 term there. The y2 term there. That's all I really need to know. Everybody with me? And then, compute at the end. Okay. All right, real nice little time saver. Now, just as a reminder, it is easy to lose track of, wait a second, what am I taking partials of? So again, make sure to label everything. A lot of people will write this, and then they'll write this, and then wait a second, a partial, what's the partial of y1 with respect to anything? Do I have a formula for y1? Where's my formula for y1? Real easy to get lost, right? So in order to emphasize that what comes out of F is what then goes into G, I like to actually say so that these things here are my y1 and y2. They're going to be going into there. And so, when I get down to computing partial of y1, then I can see explicitly right there. There's my y1. I've labeled it. Yes.
But in this specific case, in the formula for G, Y2 doesn't really affect Z2. So can we just leave out that term?
Y2 doesn't affect Z.
Yeah,
Oh, yeah. No, so you're pointing out that I got you. That the way that Z2, there's Z2, right? How that Z2 depends on Y2 is, well, it doesn't. Yeah, no, so what's going to happen there is that partial derivative is 0, and so you can see that right there. Yeah, so now, can you just leave it off? Risky move, dangerous move, right? Because it's not a question of, again, it's not a question of whether you get answers, right? It's a question of, does your argument as written make sense? Now, if you eyeball and say, oh, I can just look at that and see there aren't any y2s in there, and so I know this partial derivative is going to be 0, or there is no path, blah, blah, blah. You now have to explain that in words, right? And because you can't just not put it there because it doesn't affect the answer, because that's not the point, right? It's not about the answer. So I would rather just write down the algebra and it's 0, no further discussion required. Right? You did all your due diligence. You identified all the relevant variables. You computed. Good news happened. That's not your fault, right? But yeah, you don't want to have to write a paragraph in exchange for a term. I think it's a bad trade. Is everybody good with that? Everybody see that? It's a great question. It's a good excuse for me to talk about, this thing I like to talk about. Yeah. All right. Okay, yeah, so make sure to label, what your Y's are, and also, just to be clear, what your Z's are. All right. So confusion of variables is a surprisingly dangerous situation here. Can I fit all this? Oh, it doesn't quite fit. Okay, oh well. I was thinking I could make it huge. Yeah, so I'm going to show you a single variable version of this, and I know y'all wouldn't do this in a single variable problem, right? But what students are surprisingly prone to doing is morally identical thing in the multivariable context. So let's see what it would look like in single variable and kind of laugh at it a little bit, and then heads up, don't step on that landmine in multivariable. So here's a couple of functions. There's nothing wrong with these functions, perfectly decent functions. I say I'd like to compose them. Well, there's nothing wrong with wanting to compose functions. Fine, sure. And with these functions composed, giving me a new function, I say, what's the derivative of it? Nothing wrong with that at all. Right? The problem comes up if you're a little too hasty, right? With your calculation, and you kind of compactify and say, well, the derivative of a composition is the product of the derivatives, well, the derivative of that function is that. And the derivative of f is that. I mean, it is, right? I mean, it's algebra, and then you multiply those together and you get an answer. And this is, of course, way wrong. So different points of view on what went wrong here. A point of view is that, well, this G prime has to be evaluated at the output value of the other function. And sure, right? So, you can say that the derivative of G is 3 times something squared, right? But just don't forget, the thing that goes in there is f of x. That's the thing that has to go in to g prime. And so it's not 3x squared, it's 3x squared squared. So look, you can do that, and I guess that's reasonable, but I find that confusing too. Right? So I think it's much easier to just say, well, let's just make the problem, the thing that's causing the confusion, let's just make that go away. And then just answer the easy question, which is much better phrased. So specifically, I'm going to take this function f here. I know I'm going to need to give a name to its output value. So let's call that output value y. And now, wait a second. What comes out of f needs to be the thing that goes into g. That's not how this is written right here. Right? If I'm going to be thinking of y as the output variable for f, then y needs to be the thing that goes into g, not x. So this is what we call a confusion of variables. X is, once I've decided that I'm going to compose these functions, x is now pulling a double duty. I've got this playing the role of the thing that goes into f, but it's also playing the role of effectively what comes out of f. Right? And you just can't do that. So much better to just rewrite g, right? Perfectly fine to leave f in terms of x, but let's rewrite g in terms of, well, y, because y is what comes out of f in the first place. So just rewrite as g of y equals y cubed. Same function. Didn't really change the function at all. I'm just changing the variable that I'm using to represent it. And then you could be as sloppy as you want. Derivative of a composition is the product of the derivatives. Cool. No problem. Don't worry about, oh, yeah, but I have to plug this into that. No, the variables do that for you automatically. See, there's this y there that I've already got written is x squared. So the notation, if you don't confuse your variables, the notation will do that bookkeeping for you. And it's like the difference between stepping over a landmine versus walking along a different path that doesn't have any landmines on it. It's just there is no problem to be avoided. Okay, everybody good? All right. So again, I know y'all wouldn't do that in a single variable calculus context, but in a multivariable context, it is surprisingly easy to look at this and say, okay, I want to compose them, and to spend so much time thinking about oh gosh, I've got to take various partials of what with respect to what, and then I get these matrices, and wait a second, which order do I put them in, and which one's acting for so many other things that you have to be thinking about. They just kind of, whoops, I accidentally confused my variables, right? I mean, the functions are even given to you with the variables, pre-confused. Not that there's anything really intrinsically wrong with that. I mean, when these were written down in the first place, there was no desire expressed yet to compose them anyway. So it's not even the fault of the question writer. So anyway, I suggest that y'all be super heads up to the possibility of, wait a second, has circumstance created a confusion of variables problem for me? And when you find that, yes, it has, then fix it. And before you do any calculus, fix the confusion of variables, and then again, go on your merry way, and there's nothing to worry about. So f is written in terms of x and y. It's going to have to have some output variable names. I'm going to call them u and v, but with u and v being what comes out of f, that's also going to have to be what goes into g. And so notice I'm rewriting g, same function, just rewriting it in terms of a different dummy variable, appropriate to the naming conventions that I've got going here. Everybody good? And now there's nothing to worry about. You don't have to keep track of, wait a minute, where do I evaluate which matrix? It just kind of all goes through. Here's the DF matrix, and then here's the DG matrix. And notice DG is written in terms of U's and V's. And let's see here, I've got to multiply the DG matrix times the DF matrix, and it does remain, of course. You do have to make sure to get those in the right order, and it is real easy to accidentally get them switched. And of course, that's a big problem. And your answer is wrong, etc. But point is, you can focus on things like that and not have to worry about, did I evaluate these in the right places? Because the variables, again, do it for you. U in particular, what is this U? Oh, well, U is the first output variable from F. It says right there, U is x squared plus y squared. All right, well, plug it on in there, no problem. Wait a second, there's a V over here. What do I do with that V? Oh, yeah, well, V is the second output variable from F. And again, already labeled right there. V is x squared minus y squared. So I didn't have to remember to plug that in. That was unavoidably, unavoidably there because of the choice of notations that we set up. Yeah. All righty. So let's talk about second derivatives. This tends to not come up in single variable chain rule discussions because it's just not, I don't know, circumstance. It just doesn't really, it's not really a necessity, but it's surprisingly important when you're talking about a multivariable context. And I'm going to give you an example why later. But let's suppose that you have a composition. Right, well, I guess I better do it like this. You have a composition. So Z is a function of X and Y, and X and Y, of course, are functions of R and theta because that's how polar coordinates works. Okay, so we have a composition here. And effectively then, Z can be thought of in the composition as a function of R and theta. And in that case, how would I compute this second derivative? Second partial of Z with respect to R. Okay, so, we proceed as usual. Z is a function of X and Y. X and Y are, oh, come on, colors. X and Y are functions of R and theta. So now I'm interested in computing the partials of Z with respect to R. There's Z, there's R. I've got two terms for the, as I do the first derivative. So a couple of terms, and you take some partials, and no problem so far. Everybody with me so far? Where it gets weird is a little further. Well, let me just do it like this. Eventually, as I'm taking the second partial, notice I'm going to need to be taking an R partial of my existing partial with respect to R. So I will be taking the R partial of ZX. And where is ZX? And how do I take an R partial of it? And that's confusing, right? I don't see ZX on my picture. Not clear what you're going to do there. So the big thing to remember is that your Z being a function of X and Y, well, then its partials are also functions of X and Y. And so label them thusly on your diagram. So we're going to expand the diagram to represent that. Here's our original diagram, but now we are going to directly represent that the partials of Z are also functions of X and Y. Here, let me just do it like that. And there they are on the diagram saying so. Okay. So how do you take, well, I'm getting a little ahead of myself here. Let's, now that I have them on the diagram, let's just go ahead and proceed. And let's see here, partial of Z with respect to R, we already computed. Taking the R partial of that. Conveniently, we got lucky. And since we're taking a partial with respect to R, notice that that means that theta is a constant, and that means cosine theta is a constant, and therefore I get to, kind of pull out the cosine theta. Likewise, the sine theta, all constants. And then here's the big moment where I'm taking now the partial of Zx with respect to R, which previously, again, looking in this diagram up here, where is I don't see Zx. How do I take a partial of Zx with respect to, what does that even mean? Well, no problem. Now there's Zx and there's R. And I can see right away that there's two terms. Apparently X is an intermediate variable, thus giving me that term. And so it seems, thank you diagram, Y is an intermediate variable, and that gives me that term. So just straight up intermediate variable chain rule. Okay. All right, I'm out of time. So I'm going to come back and say some more things about this next time. So I think, where am I going to draw the line? I guess I'll figure that out later. But anyway, you all have a good day. I guess I might as well remind you, don't forget we have an exam on Friday. So good luck. Study hard. No, in fact, since I haven't finished 2.5, and since I am even less likely to finish it in the other classes, because I'm a little further behind, I don't think it's likely that 2.5 will be on the exam at all. Well, I'm not saying for sure yet, but it's not looking good right now.
When will we know for
Yeah.
sure?
When I supplement this schedule here, right, when I fill in this cell,
Okay.
and if as I expect, you see the dash, that means officially not part of the material. Yeah. Okay, so we'll see. Okay, see y'all later. Give me a second to just stop this share. See y'all later.